So far, we have learned what electricity is, and one way in which it is produced. Now, we come to magnetism. Magnetism is important not only because it's the basis of the navigator's most important instrument, the compass, but also because it provides the engineer with the means of producing electric power on a giant scale. A simple definition of magnetism is that it is the power to attract. This magnet attracts, for example, iron or steel objects, and they are referred to as magnetic materials. All magnets are not shaped like this horseshoe magnet. Very common are bar magnets like this one. Surrounding a magnet is the space in which it affects magnetic materials, and this is called the magnetic field, or the field of force. We can demonstrate this magnetic field quite easily. We put a thin piece of glass over the magnet and sprinkle onto the glass some iron filings. It may require a tap, but the iron filings will set themselves into lines forming a definite pattern. We talk of lines of force. Although by this simple trick with iron filings we made the magnetic field visible, the lines of force are really quite invisible. Another striking effect of a magnet is that if we hang it up in such a way that it can rotate, it will always set itself to point in a certain direction, and that direction is toward the north. This property of a magnet is the basis of the magnetic compass, on which all navigation at sea depends. A magnetic compass needle always points the same end to the north. We call that end the north-seeking pole, or just the north pole of the magnet. The other end is, of course, the south-seeking pole, or south pole of the magnet. The reason why magnetic needles behave this way is that the Earth itself behaves as if there was a huge magnet at its center, with its end pointing approximately, but not exactly, toward the north and south poles of the Earth. In the same way as the compass needle, a bar magnet has north and south seeking poles, or just north and south poles. All magnets, whatever their shape, have north poles and south poles. Coming back to the magnetic field, we give the lines of force a direction and say that they emerge from the north pole and re-enter at the south pole. Similarly with horseshoe magnets, the lines of force are packed close together near the poles, and the field is very strong between them. All the magnetic strength of the horseshoe magnet seems to be concentrated around the poles. This is true of a bar magnet as well. There seems to be no magnetic force at the center. If we put a piece of magnetic material, say iron, in the magnetic field of a bar magnet, and produce the picture of the magnetic field with iron filings again, we see that the lines of force have concentrated in the iron, and it has itself become a magnet. We say that magnetism has been induced into it, and we call the process induction. An interesting case of this is when the hull of a ship in the builder's yard lying in the Earth's magnetic field has magnetism induced into it. This has to be got rid of by the process called degaussing. When the piece of iron is taken away from the field of the magnet, it loses its induced magnetism. It was only a temporary magnet. More lasting magnets can be made of iron, but they do lose their magnetism rather easily. Steel is used for permanent magnets, and they're very much more powerful than magnets made of iron. Some alloys of steel also make strong permanent magnets, and they come in for a lot of uses in electrical machines and electrical devices. If now we take a bar magnet, its north pole is painted red, and bring another one up to it so that its north pole is to the south pole of the first one, the two magnets attract each other and come together with a snap. Not really very surprising, you might think. But what about when we bring the two magnets together so that the north pole of one is toward the north pole of the other? Well, they'll have nothing to do with each other and drive each other away. The principle is that like poles repel each other and unlike poles attract each other. This is the great law of magnetism. Like poles repel, unlike poles attract. The iron filings demonstration makes this clear. When unlike poles are together, the lines of force join up into one field. It is very strong between the adjacent poles. On the other hand, when like poles are together, the lines of force turn away from each other and almost seem to be pushing each other apart. There is a region without lines of force between the two magnets. And that's all we wish to say about magnetism for the moment. As we progress in our study of electricity, we shall find that these few simple facts about magnetism have a profound influence on how the forces of electricity are harnessed for our needs.